recording here my screen, and I will upload this video to my YouTube channel. Let me start sharing my screen as well. Okay, here's the situation. I corrected homework 6 and exam 3 and uploaded it to your folder. Uploaded them to your personal folder. Okay, and let's take a look at the schedule here. In the syllabus, we go today. Okay, we'll continue electricity. Homework 7 is due today. Homework 8 is due the day after tomorrow. I understand that homework 8 has lots of questions there, right? So let's take a look there. Homework 6, homework folder, homework 8. Let's see. Yeah, we have 93 questions. Okay, so I'm leaning towards make it as though as it's 2 homeworks. So I'm gonna give like a weight of 3 because it's 3 times as much work as before. Okay, so it gives you a motivation to work on that. Okay, so let me write that down here. Homework 8 has homework 8. Let's see. This due. This homework has a weight of 3, and the other homework is just a weight of 1 because there are lots of problems in there. Is that clear? Let's do it this way. Okay, so and what else we have to do? Okay, we're gonna finish electricity here, and let's see where we start. We are going to start talking about the Ohm's law. Here you go. Ohm's law. Oh, we start talking about Ohm's law. Chapter 8. Electric voltage, electric resistance, Ohm's law. Page 194 here in my book. 193, 94. Yeah.
Professor?
Yes?
Oh, yes. Yeah, I saw my grade for homework 6, but I don't see exam 3.
You don't see exam 3 there? Let me check. Anybody else has a problem or just Blaze? Let's see, Google Drive. Google Drive. Again, did you refresh your screen, Blaze? Make sure you refresh your screen, right? Sometimes it takes, let's see, homework 3, exam 3. Let's see here. Yeah, it's right in here, Blaze. You see that? Homework 3A. Exam 3A. Here you go. Homework 6 is here. Exam 3A is here. Okay. And I uploaded like right now at 3 o'clock, 2:57 p.m. Do you see it there now, Blaze?
I'll refresh I'm refreshing the screen now.
If you still cannot see, just get out of your browser and go back there.
I see exam 3A now.
Okay, good. Okay, so that's resolved. Okay, so here we go. Here is the relationship that you gotta know. There's a relationship. This relationship applies to many types of elements in a circuit. And you saw a resistor. Did I show you a resistor before? Let me give you that demonstration again with the resistor, the battery, and the LED, right? Let me put my stuff together here. a shame. I can't find my battery. Oh, nope, that's not this one. No. Yeah, it looks. Let's see, this is my desk. No, it's. Oh, here you go. It's my desk, right here, the battery. Let's get my resistors. I'm gonna get different types of resistors right now, so you can see the difference in the intensity of the light. You know, there's a bunch of resistors here. LEDs. I need my battery. Oh, not this one. Not this one. Here you go. That's the one. And then I need my LEDs. Let's get this one here. Man, it's getting hot here. And I'm gonna get my proper board. Here you go. Okay, let's work on the Ohm's law. That's the idea here. Continuous electricity, and what else we're going to do? Let me just give you, yeah, an idea what we're going to do. Okay, electric. Okay, good. So we're going to do the following. Here you go. Today we continuous electricity. We will. Here you go. Elaborate Ohm's law. Okay. Look at the electric circuits. Look at electric circuits. Types of electric circuit. Types of electric circuit. Parallel. No, first in series. That's the simplest one. Series and parallel circuits. Those are the two important ones. And what else we're going to do? We're going to look at the electric power. Okay, so that's what we're going to do today. So let's start on Ohm's law first. I'm going to give you an idea of how Ohm's law looks like visually. Okay, visually first, and then I will give you an idea how Ohm's law looks like mathematically. So what we're going to do, I'm going to power here I'm going to put my battery in my circuit, and I'm going to connect a resistor to my circuit. First, I'm going to start. Think about that, folks. Here you go. Take a look at this relation here, okay? Let's give you a going back to Ohm's law. Going back to Ohm's law. Okay? You have V equal to Ri. Okay? So here you go. This relation can be written differently, right? You can write that as being I equal to V divided by R. Okay? So, what does it say? It says that, what this relation says? This relation says that if V increases, okay, the current will also increases. We can go the other way too. We can go the other way, that if V decreases, the current of the circuit also decreases. What else can we? And that in case that the resistor is the same, right? In order for the voltage to decrease or increase, what we have to do? We have to get a different battery that has a higher voltage. If this battery is 9 volts, we'll get a car battery that's 12 volts. Okay, or another battery that's 24 volts, and so on. We're not going to do that here. We're going to do something simpler, easier to do. I don't have different batteries here for us to change the voltage. So what I'm going to do? I am going to change the resistor, because I have a bunch of resistors here. I'm going to keep the voltage constant, okay? And I'm going to change the resistor. If I increase the resistance, then the current should decrease. Similarly, if I decrease the resistance, the current should increase. Okay? How do you, if you cannot measure the current, there is the next best thing. The next best thing is just by looking at your LED, how bright it is. Okay? Here you go. If you cannot measure the current, that is the next best thing. The next best thing is to observe the intensity of a light source. When the current increases, decreases, then the intensity of the source should increase, between parentheses, decrease. That's what the current does. The current makes a light source shine brighter. Okay? And you must be careful. You must be careful, because if you exceed a given current for the source, you can even burn the source. Okay, I have done that many times. I was not aware of this problem with LEDs, and I was burning out my light sources over and over again in a project of mine. Okay, at this very moment, we don't have any resistance there whatsoever, so I'm connecting my LED directly to my battery. That should be the highest intensity that you can get. Okay, the highest possible intensity that you can get in an LED, because there is no resistor whatsoever being connected between the LED and the battery. Okay, so just go ahead, take a look at, gauge how much the intensity is with your own eyes. It's going to be a qualitative, of course, it's going to be a qualitative perception, right? There's no, I'm going to look at that too. And then what I'm going to do, let me get here, I wonder if it's going to be able, I'm going to get a resistor, 270 ohms in this case. I'm going to connect to this circuit, and hopefully we are going to see a change in the intensity compared to the other situation. Here you go. My LED is here. LED has a leg that's longer than the other. Okay, the longer leg should be connected to the positive of the battery. Very important. An LED is a device that has a polarity. If you connect on the other direction, the LED is not going to light up. Here you go. So remember, remember that. Let's see if this thing here is not going. It's not getting secure there in the hole. Let me see if I can get better. Oh yeah, now it's better. I can feel it. Now I'm gonna put my battery, and hopefully we'll be able to see a difference in the intensity. Now take a look. Okay. I'm going to remove the resistor in the circuit, and you're gonna look again at the intensity of the light. You know, when I do something like that, you know, it is as though as I have a zero resistance. Do you see the light intensity? I'm gonna put the resistor back in the circuit. You know, and it's clear. It's clear that without the resistor, the light is more intense, right? So what's happening here again? What's happening here is that the resistor is decreasing the current of the circuit. Okay, and we can gauge it just by putting a light source in the circuit and observing the intensity, how it looks like. Right now it's very intense. Right now it's so intense that the light even becomes yellowish. I can see that. Oops. It's not, something is happening here. Let me bear with me. Here you go. Yeah, okay. So here you go. Take a look again with the resistor. Without the resistor, far more intense. Okay. This is a 270 ohm resistor. So that's a good gauge of the effect of the resistance in the current in a circuit. Okay, 270 ohms, I can go to a lower resistor, and you should see that the intensity is going to be higher. 270 ohms in this case, and now I'm going to replace this 270 ohm resistance with a resistor of 10 ohms, 20 times less the resistance of the other. Okay, so here you go. Okay, take a look. Okay, compared to the other one, it's more intense because the resistance is less. Okay, so that's one way of gauging the current. Another way is to measure the current using a device. There are cheap devices out there that can measure a current. Okay, or an ammeter. An ammeter can also be used. An ammeter can be used to measure the current in a circuit. Okay, this an ammeter. Here you go. I'm gonna a rather inexpensive device can be used to measure the current in a circuit. Okay. As stated above, you can also gauge the intensity, the current in the circuit, by putting a light bulb, a light source. It doesn't have to be a light bulb, right? It can be a light source. Light source. If the intensity as the current increases, the intensity of the light also increases. So that's one way. It's getting very hot here in my room, man. I'm gonna turn on my air conditioning very soon. Okay, so let me give you an example, a numerical example. Suppose now I just remove my light bulb from here. Oh, you know what? I'll keep it. I'll keep it. Yeah, I'm gonna remove it. I remove my light bulb here, and I come up with the circuit right in here without the light bulb. Here you go. I'm gonna connect the battery to the ends of this resistor. Because I don't have a light bulb, I won't be able to see the light, okay? Here you go. Okay, now I got it. Here you go. Now I have a circuit again without the light bulb. Since there is no light bulb, we are not able to see a light there shining. But you should understand that there is still a current in this circuit. We cannot visualize the current by the light bulb through the light bulb because there is no light source in there. Oh, and by the way, my resistor is becoming so hot here. Yeah, I gotta be careful. Yeah, I gotta take out this resistor here. Wow, that's so hot because this resistor is very low. I gotta put a more intense, higher resistor there. Otherwise, I'm gonna burn my resistor. I could feel it. The resistor was very hot because the current was very high. Now, what about now? Let's take a look here. This one should be a higher resistor. I can feel a little bit of heat here. Okay. Not as much as I used to see with this one. Why is that? Because this resistor here is a low resistor. A high current produces more heat than a low current. Okay. Now because I put a higher resistor here, I don't feel as much heat here. That's another way of gauging the amount of current in a circuit. Okay, and let me give you make a drawing for you how we usually represent this type of circuit. I have an illustration here. Here you go. That slides. Bear with me. Resistors in parallel, two resistors in series. Single resistor right in here. Okay, so here you go. Oh, here you go. That's how we represent a circuit with a single resistor. That's how we represent. That's the schematic of a circuit. This circuit right in here. What you see right in here is the voltage, is the battery, is the source of voltage, a battery, my 9-volt battery, for instance. And what you see right in here is the representation of the resistor. The resistor is represented by something like that. That's the representation of a resistor. Okay? So, at this very moment, we have a current flowing through this circuit of mine. Electric charges are moving in this circuit of mine, just like you saw in that simulation that I showed to you. Here you go. And we can calculate what this current is. We can do that. Let's do that. Okay? So let me get, we use Ohm's law to calculate the current. I'm going to get my favorite computer program. Here you go. coming online. Ohm's law. Now we're going to talk electrical circuit. Electrical circuits. Okay, Ohm's law. Ohm's law. So assume that in our case we have a voltage source that's 9 volts. And we have a resistor that's 270 ohms. What do we want to do? Find the current. Find the current. Okay? That's what we want to do. Given a power source of 9 volts and a resistor in the circuit of 270 ohms, find the current in the circuit. We go ahead, we use Ohm's law. Okay. We want to find out this value here, this current. Here you go. User defined. I want to do like that. And here you go. I'm going to substitute V and I'm going to substitute R. Let's not, here is the unit, V divided by omega. Okay, V divided by omega is amps. V divided by ohms, volts divided by ohms, is equal to amps, according to Ohm's law. I can substitute right here in this equation, and we get my current. Calculate 0.033. We're talking about 33 milliamps of current. That's 300ths of a ohm of an amp, 300ths of an amp, or 33 thousandths of an amp. That's the type of current that you find in your cell phone. Okay, that's a regular type of current. It doesn't exceed 100 milliamps. Doesn't go higher than 3 times this value. Okay. So if you double the resistor, what happens if you double the resistor? You're going to bring down the current. I'm going to double to 540. Here you go. Here you go. The current went down by half. We were at 270, right? Here you go. If you cut down the current by half, 135, the current doubles. And so on. That's the type of behavior of the current in a circuit. Okay, so here you go. That's how you should visualize a current flow in a circuit. That's the symbol of a battery. Okay, that's another drawing here. That what you see right here is just like my power supply. Okay, my power supply is just like my battery. This device that you see here in the screen is just like my green battery. It behaves like a green battery. And here's the symbol that I did for my resistor. Okay, but in a schematic fashion, we represent that like that. Current flows from the negative to the positive in the circuit. In this case, it's clockwise. Okay. So we still have current flowing here in my circuit. Did you get an idea how Ohm's law works? Okay. What I'm going to do now, we have time, right? We have kind of some time to work here. I'm going to get my multimeter. I'm going to show you the value of the current flowing through through the circuit. Hopefully my multimeter is working. My current, my ammeter in the multimeter is working. Okay, so hang in there. I'm going to show you how we measure those things. And by the way, I'm going to turn on my air conditioning because it's becoming hot here. you go. I have a bunch of multimeters here. I have what, 3 or 4? I have a total of 3. If one doesn't work, because sometimes those guys burnt out, okay, and they may not work. So I would just use another one. Let's see. That's the device I'm talking about. It's a multimeter. We have a bunch of those there at the college. They're rather cheap. You know, you can buy cheaper ones. Their price range anywhere between $15 to $1,000. Okay, this one here cost me $15. Now, you know, I couldn't find them by $15 anymore. Now they're selling the same multimeter by $30, made in China. But the $30 multimeter has a nicer package, has a nicer case. You know, this case here is looks like very flimsy. You know, that's why they were selling by $15 only. But later on, when I went to look for this model again to buy a $15 multimeter, they changed it. The casing, it looks exactly like that, but the casing looks nicer now. The same colors, the same design, but it doesn't look like that. It looks like materials that is much better. And they increased the price from $15 to $30 just by making it look better. Okay, so here you go. I'm gonna measure the current. I'm gonna turn it on. Hopefully my ammeter is not burned out. We are going to find that out very soon. Here you go. Gonna put my circuit together. Let's see here. Let's see how we're gonna do that. Oh, I'll need to do it in a different way. This probe is not gonna work. Bear with me. No, not this one. It's not gonna work. Nope. I'm not prepared for doing a nice demonstration of that, unfortunately. Let me see, maybe this one? Nope, not this one. Not this cable. I may have some of the cables here. Let me check. Yeah, this one might work better. Yeah. Okay, so here you go. A different cable. Convenience, just for convenience wise. Unfortunately, let's see if I have something black here. Nope. Yeah, I'll have to make do with whatever I have. Cables. See, alligator. I was looking for an alligator like that. So this one is gonna go right in here. And this one is gonna go right in here. So let me show you what I'm doing. Here you go, I'm connecting my multimeter to this circuit. What am I doing? Let me show you exactly how it looks like in a circuit diagram. Here you go. Something like that. No, not this one, sorry. This one is a voltmeter. Let's see here. Yeah, it looks more like that. Okay? Here is my multimeter. That looks different, but it's the same thing. And in a circuit-wise way, you put the ammeter like that. Let's see if we can measure the current here. Yeah, we can measure the current. I'm going to show you the current. Here you go. See, 15.97 milliamps. Here you go. 15.92 milliamps. If we change the resistor, we should change the current. Let's get that. I'm gonna put that small resistor. Hopefully it's not gonna burn anything here. You see, oh, I disconnected this. Note, see that when I disconnect this circuit, the reading goes to 0, right? When I disconnect this circuit, here you go, the reading goes to 0. Go back here. You need to get, a measurement of this resistor. Now I'm gonna put my 10 ohm resistor, the one that was warming up before. Here you go. Hopefully I'm not gonna burn my multimeter. You gotta be careful with that. Yeah, it looks like you see the number 1 here. The number 1 here means that I'm using too high of a current of the multimeter. So I've got to change the scale. And I may be able to make a measurement. Oh yeah, look here. 230 milliamps, 0.23 amps. Because I have a very small resistor there. Okay? So, and going back, 0.22 milliamps, going back to the previous resistor. Okay, see, my resistor is already warm. Hot. Now, oops, I gotta go to another circuit here to measure my amps. 14 milliamps. Right, it's almost half as we had before. The other one was 230 milliamps. Now, oh wait a minute, 230 milliamps is 10 times more. It's not half, it's 50 times. 50 times less. Okay, and let's just measure this resistor. I'm suspecting that it's not 10 amps what I have here. 10 ohms what I have here. What I have here is what? Ohms. I can measure my resistance. Go. Oops. Okay, this guy here is 266 ohms. So close to 270. Close to 270. Okay. This resistor. And the other resistor is let's see, just like 10 ohms. Yeah, close to 10 ohms. 270 and 10 ohms. Now, I am suspecting that my battery is not 9 volts. I'm suspecting, let's see what's the voltage of this battery. I'm suspecting that the battery is a little bit less than that. Let's check it here. Oh yeah, I lost lots of power in my battery. See that? Lots of voltage, lots of energy. It's not 9 volts. It's 4.7. It's half. I gotta recharge this battery again. So those currents that you're seeing was less than what you had predicted in the equations because my battery became discharged, okay? And Here you go. And I was getting a lower current. So here you go. I'm going to put here 4.74 volts. 4.74 volts instead of 9. 4.74 volts. And when we use, I'm getting 0.0. Let's see, what is the volt? What was the resist? Oh, I'm putting 135 here. Let's put 270. I'm getting 0.017 amps. And we got like 0.014, right? That's what we got before. Let's put that again. Must be this one here. Got and I got to change my those cables are not good. Yeah, I'm getting 15 milliamps. My equation said that 17 milliamps. So there is a little difference, 10% difference. Almost 20. A little bit more than 10. It's 2 milliamps out of 15. You know, it's like more than 10%. It looks like it's 15% difference. 15%. Wow, what I predicted in my equation was 17. Okay, so let's put. I was measuring 266 actually, right? 266. Let's see. It doesn't. Yeah, it doesn't change much. It doesn't change much. But there's a 15% difference in the amperage. It's possible that the battery is becoming discharged quickly. You know, that's why we're reading a lower current here. But that's how we do. Okay, the equation for Ohm's law works very well in real life. I do this experiment over and over again with my students in the lab, and we get a very good match between experiment and theory. Right now, I get matches even better than what I'm getting right now. Right now, we're getting like 15% difference. We usually get less than 5%. Right now, we are getting lots of error, a large difference because my battery is becoming uncharged, discharging very quickly. I gotta go back and recharge it. That's what I want to show you. And so that's how things work in real life. Put it back here. My resistor, 70 ohms. I'm going to get this thing organized back in my put that away. That's 70. Okay, here you go. Clear up my desk, and I will use that later on. Okay. And now what we're going to do, you already saw how to, this circuit that you saw, this circuit that you see right in here is the simple circuit that you're going to see in your life with a single resistor. But you can have a circuit with 2, 3, 4 N resistors. You can have. Okay? And there are two ways that we can connect elements in a circuit, either in series or in parallel. Let's go. Well, first we saw a single resistor in a circuit, but we can also have 2, 3, or more elements in a circuit. Let's stick to resistors. That's the simplest device that we have out there. Okay. The way we connect electrical elements, okay? Electrical elements, I mean what? I mean a resistor, light bulb, etc. There are two ways. Here you go. There are two different ways we can connect electrical elements in a circuit. Either in series or in parallel. There's another way, but you don't need to know about it. For the sake of this course, just remember circuits in series and circuits in parallel. That's all. Okay? I'm going to show you how you connect two elements in series. Okay? When one element is right after another one, we say they are connected in series. Okay? I'm gonna show you how they look like in real life again. My battery, right? Here you go. My battery connected right here. And I'm gonna get two resistors. Let me stop sharing so you can see my image better, right? Here you go. Here you go. I'm gonna connect my battery here to this breadboard. Okay, and then I'm gonna put two resistors in series right now. Right now I don't have a circuit because there is no element there inside here, this breadboard. I'm gonna get two resistors. I'm gonna connect them in series. Here you go, one resistor. And I'm going to connect another resistor. Here you go, a second resistor. How do we connect them in series? We touch one end to the other one, like that. And what else? I have to close the circuit. Here you go. I gotta connect this guy to the other end of the battery. We do that by connecting them in the same row that we have here. Right now the circuit is open and there is no current passing through it. But however, if I touch this end of the resistor to the other end of the resistor, now we have a closed circuit. We have two elements in series in this circuit. I'm gonna organize it better. Here you go. I'm gonna put the battery here at the end of this battery so it can look nicer, okay? There's nothing wrong what I did there before. I just wanna show you a more organized way of showing the circuit. Here you go. Oh. This guy is getting out. Okay, now it should stay there. Okay, here you go. And now I'm gonna touch the two ends of this resistor and we get two resistors in series. Okay, another way of putting those resistors in series, more a handier one, is just by putting here in the breadboard. Okay, note when I connect something like that, it is as though this end is connected to this other end. Okay, so what we have here, we have this black wire from the battery connected to this end. This end of this resistor connect to this left end of this other resistor, and finally we close the circuit by putting the red wire right here. Okay, right right, like that. In a graphical, in a schematic sense. I'm gonna show you. I'm gonna start sharing my screen again. Here you go. In a schematic sense. Here you go. Must be this one right in here. Let's see here. Yeah, two resistors in series. See that? The two resistors are in series. That's my breadboard. One resistor connect to the other one, and then we connect the battery to those two ends. Okay, here's the battery. That's the schematic. If you want to measure the current going through the circuit, you connect a multimeter right in here. Okay, here you go. That's how the current flows. There is something interesting about resistors in series. When you connect two resistors in series, those two resistors behave like a single resistor, having a resistance equal to the sum of those two. I'm going to put that in my notes, okay? When you connect two resistors in series, these two resistors behave as though they are a single resistor with a resistance equal to the sum of the two resistors. Example, okay? Example. Let one resistor of 10 ohms be connected to a second resistor of 30 ohms, okay? Be connected in series, okay, to a second resistor of 30 ohms. Here you go. Oh. What is the resulting resistance? Okay. Oh, it's the sum of those. Solution. Okay. The resulting resistance is the sum of the above resistors, or 40 ohms. Okay, that's how they behave. So right now, those two resistors are behaving as though they are a single resistor that has a resistance value. That's the sum of those two, the resistance of those two elements. Okay, so when you, oh, here you go, gotta do something about that. Someone is in here. Okay, Brian. So when you connect resistors in series, you always get when you connect resistors in series, okay, the resultant resistance is always larger than the highest resistance value. You know, because they sum, right? Why is that it's highest? Because they sum with one another. That's an important property of circuits in series. Okay. if the resistance increases, okay, if the resistance increases, right? So the current must go down. Okay. Let me get another illustration here for you. Loading. Let's go. I have this PowerPoint with 400 slides. Let me see if I can get it. No, not this one. Here you go. That's a complicated circuit. You don't want that. Let's see. Let me see if I can. Oh, yeah. Okay, so here you go. Here's an illustration of two resistors in series. Okay, here you go. I'm going to make it easier for you to understand. Here you go. Let me see if I can get that. No, yeah, let's do it this way. Here you go. That's a circuit with a single resistance. That's a circuit with two resistances. Now the battery, I inverted the polarity. When we have a circuit with two resistors, I'm going to make it simpler. Here you go. We're going to talk about this V1 and V2 later on. When you have this circuit with two resistors, they behave as a circuit with a single resistor. Like that. Here you go. Here you go. That should be R1 plus R2. That's what we call equivalent resistance. Like that. I'm going to do even better. Here you go. Bring this guy down. Get the other one. Here. Oh, I'm going to put my V right in here. Oh, I'm going to put this V here. I'm going to put this R1. Oh, stay that out of the way. R1 here, R2 here. Okay? So this circuit behaves like this circuit right in here with a single resistance having an equivalent resistance that's equal to the sum, R1 plus R2. What else you have to know? You have to know something else too. Okay, so here you go. What you have to know, and something else that you have to know, is right in here in this figure. Not only the resistance are summed up, but the voltage is split as well. Okay. See, we have a voltage here. My battery, let's see, is providing 9 volts. So when my battery is provided, don't forget, what we have here is energy that's being provided to this circuit. So if you have a battery of 9 volts here, this voltage being provided to the circuit is going to be split between those two resistors. Okay? So if you have 9 volts here, you can have 4.5 volts here and 4.5 volts here, assuming that the resistance are the same. If this resistance is more than the other one, you're going to have V2 greater than V1. Okay? So here you go. You can write down like that. V is equal to V1 plus V2. V1 plus V2. So when you connect resistors in series, the voltage, the energy is distributed between the resistors, either, in principle, unevenly. Okay. Something else that you have to know. So let's go. The resistance increase, so the current must go down. What else you have to know? What else you have to know? Here you go. Well, you have to know that the voltage from the battery gets split among the resistors in parallel. I'm going to give you a numerical value, okay? So here you go, a numerical value. So, example. Numerical example. Okay. Two resistors are connected in series to a 9-volt battery. Okay. If one of the resistors is using up 5 volts, how many volts is the second resistor using up? Okay. Okay, solution, remember, V must be equal to V1 plus V2. Okay, here you go. For resistors in series, here you go, for resistors in series, the voltage across each resistor sums up to the value of the battery. Okay? Or insert, let's go get it, here you go. V is V1 plus V2. V1 plus V2, okay, here you go. The voltage provided by the battery is 9 volts. And we know that one of the resistors uses up 5 volts. How many volts does the second resistor uses? It's 4 volts. It's just the complement of the other. V2 is going to be equal to 9 volts minus 5 volts. Here you go. Which is 4 volts. Okay. What else you have to know? Okay. The resistance with the highest, the resistor, here you go, with the highest resistance value uses up the most voltage. So I can tell you that the first resistor has a higher resistance. use up the voltage, yeah? Yeah, okay, good. Raquel know that, right? That's great, Raquel. And use up the highest voltage according to Ohm's law, by the way, okay? You can use Ohm's law. You can use Ohm's law to determine that. So those are two things that you have to know, okay? So summary. Resistors in series. Two important characteristics of resistors in series, okay? Has an equivalent resistance that is equal to the sum of their resistance. What else? Their voltage, the sum of their voltage, the voltage they use up, the sum of the voltages, they use up is equal to the voltage provided by the battery in the circuit. And that, of course, assuming that nothing else is in there. So if you have 3 resistors, same thing. 4 resistors in series, same thing. Equivalent resistance R1, R2, R3, R4, so on. And the voltage drop in each, used up by each resistor is going to be, V1, V2, V3, V4, and their sum should be equal to the voltage in the provided by the battery. That's what we have. Resistors in series has equivalent as equal, okay, and the equivalent resistance, okay, is always greater than the largest resistance in the circuit, okay? The sum of the voltage they use up is equal to the voltage provided by the battery in the circuit. There you go. I'm going to put that in generic format, okay? I'm going to put that in generic format. We usually, here you go, for the resistance, we call it the equivalent resistance for resistors in series, okay? We call equivalent resistance R1 plus R2 plus R3 plus R4 and so on. R2 plus R3. Depends on the number of resistors we have. 1, 2, 3 plus Rn. Okay. Mathematically speaking, the equivalent resistance is always greater than the largest resistance in the set, largest one, because they're summing up in the set. Let's say Rn, where you go. I'm gonna put like that. R1 is less than R2, less than R3, less than R4, R5, less than Rn. Okay? Rn is the largest one. The sum of the voltage they use up is equal to the voltage provided by the battery in the circuit. What else? Okay, so here you go. If V is the voltage in the battery, I'm going to and V1, V2, V2. Don't forget, V is like energy, right? When you have a resistor in your circuit, so each resistor is using a given amount of energy. The higher the resistance of your resistor, the more energy they use up. What else? There is one more important thing, okay? The current, here you go. The current across each element, the current across each element is always the same. The voltage is not, but the current is the same. Let me show you. So 4 important points. We're going to revisit those 4 important points when we start talking about resistors in parallel. So here you go. Let me show the drawing here. Do you see here my circuit? You know, those arrows here are indicating the flow of current. Okay? So the current flowing through the resistor 1 is equal to the current flowing through the resistor 2. Okay? The velocity of your electric charges doesn't change here. It's the same throughout the whole circuit. Okay? So what I'm going to do? I'm going to put here I equal to I1 equal to I2 equal to I3, so on. It's an important, so quite 4 points that you have to memorize. I1 equal to I2, and all of that we can see in the lab. Okay, equal to IN. Here you go. We're going to make a table of that. All of that. Okay. What time is that? Oh, 6:15 already, huh? We're going to have our break. 6:15. Break. Till, let's do,
Professor?
Yeah. Go ahead.
Oh, yes. So I have my main question is on homework 8. Basically, what does it mean if it's weighed in 3 ways?
It's not weighed in 3 ways. It's like all the homework in the past was worth 100 points. Okay. Okay. Make sense? Every homework 1, 2, 3A, 3B, 4, and so on, they are worth 100 points. Okay. Homework number 8, because we have 90 questions in there, because it's a longer homework, it's 3 times longer than the other homeworks, and also the chapter has far more information than the other ones. You know, homework number 8 is gonna be worth 300 points. Okay, that's what I meant. I'm gonna write that down here.
So
yeah.
So if it's worth 300 points, that means so whatever score I get, do I just double it to make it? Do I double it or?
No, you triple. You triple, right? You multiply by 3.
So let's say if so how would I determine my grade for that for homework 8 if it's in 3 ways?
You whatever grade you get for homework 8, you multiply by 3. If you get 90%, you know, you multiply 3 by 90, you get 270. Okay? That's how you do it. And we do what we call a weighted average. We call that a weighted average. Okay?
And basically, I can use those extra points that I get for my other tests?
No, that's not how I do it. The way you calculate, let me give an example. Suppose that you got, let's say, 90% on homework 1, right? 90% of homework. Well, what you do, Higo, come by during my office hours, and then I'll explain how we calculate that. Okay, it's a weighted average. Let me write that down for you. Okay, homework 1 through 7 are worth 100 points. Okay, like that. Homework 8 is because homework 8, because it's longer, because it is longer, is worth 300 points. Okay? So what we have, we are going to end up having 8, 9 homeworks, right? In the total, we have 9 homeworks. Okay? 9 homework. Homework 1, 2, 3A, 3B, 4, 5, 6, 7, 8. Okay? And you calculate the grade of your homework by summing the points and dividing by 11. Okay? 11, why is that? Because the weight of homework 8 is 3. Okay? That's how we. So it's homework 1, 2, 3A, 3B, 4, 5, 6, 7. And then homework 8 has a weight of 3. So you have 1, 2, 3. You divide by 11. You sum all the points of those homeworks, divide by 11 to get the average.
And let's am I allowed to exclude my lowest score on that?
Yeah, I'm going to exclude the lowest score. When I do the calculation, I'm going to exclude the whole lower score for you. So instead of dividing by 11, I'm going to divide by 10. Okay?
Okay.
Okay,
so I
add by 11, I'm going to divide by 10.
So I add the number percent wise. Let's say 90% plus 80% plus whatever up until homework 8, and then I divide it by 11.
Yeah, divide by 10, right? Have to exclude the homework, the lowest grade, and divide by 10. Let me give you an example. Okay, let me give you an example so you can do that here before we go to the break. That's what we call weighted average. Okay, let's here you go. Example, right? Homework 1, homework 2, homework 3, 4, 5, 6, 7, 8. Here you go. 3. Here gonna be homework. Let me insert this one. That's gonna be homework 3A. Next one is gonna be homework 3B, right? Okay, homework 9 and 10 are not there. Here you go, like that. Each homework has a maximum grade of 100. Maximum. Here you go, homework. Maximum grade, right? 100. Everyone has a maximum. Okay, and then we have a weight for each homework. This homework has weight 1, 1. Everyone has weight 1, with the exception of homework 8 that has like 90 problems. Okay? Like that. Maximum points, max points, is going to be what? 1 times 100, right? 1 times 100, only this one is 300. Okay? Like that. So let's say maximum grade. Suppose we're going to, grade. Suppose that you get the following grade. I'm gonna make up the grades here. 70. You got 60. We got 80. We got 90. You got 75. You get 95, 85, 60, and 95. Okay. So here you go. That's the grade of those homeworks. Now, the weight of each, weighted grade. Let's talk. Is it gonna be 70 times the weight, 60 times the weight, and so on? Okay, because this one is weight 3, you're getting to 285 points. Okay. So what's next? Okay, next we're going to do the following. I am going to drop the lowest grade of all the homeworks. Okay, the lowest grade of all the homeworks, this one is those two here, right? But I'm gonna drop only one. That's what I'm gonna do. Okay, I'm gonna drop the lowest one. So and I'm gonna sum grades, sum the grades. Okay, so sum, all the grades minus the minimum, the lowest grade, minus the minimum. Here you go, 840. That's the sum. And now we have to divide by, here you go, let's put here sum by the sum of the weights minus 1, which is in this case is 11, right? So I divide final grade, homework grade is 840 divided by 10. That's how it works. That's what we call weighted average. Okay? Okay, so how many points for the final or for the entire class? Let me see. Are you talking about the final exam? Are you talking about the final exam, Yareli?
And I just had a question about homework 8. That's all.
Yeah. But Yareli asking something else. Are you asking how many points for the final exam, right, Yareli? Is she still there? Oh, yeah, Yareli is quiet. Here you go. Let me show you the schedule here, the syllabus. Here you go. Here you go, Yareli. That's covered right in here in this table. Okay, attendance is 5%, lab work is 15%, homework is 10%, partial exam is 50%, and final exam is 20%. Okay, so if you came to every meeting, you get 5 points. If you get 100 points, 100% on all the lab work, you get 15 points, and so on. Okay. So each of those activities here, you're going to calculate the average grade of them. The final exam accounts for 20% of your final grade. So it's 627 here. So let's go for a break, right? Here you go. Break is, let's go. Break from 6:30 to 6:45 p.m. Okay? I see you soon.
Did you feed them?
Huh?
Did you feed them?
Yeah.
When?
12 noon and what, 3 o'clock?
Twice?
Yeah. Max was begging, so. It's 6. Okay, so there's still time. Looking good.
You want to eat more? Huh? Get what you want.
Yeah. Sure.
I didn't check. Go ahead.
Yeah. Why don't you go buy it? Rico, I'll be teaching until 9 o'clock today. there is this difference. Ok, 9,50. 35 10. Good. Next, 271.89. 1,000. Okay. Dois. Oh, oh, oh. You're coughing. You're coughing. I don't cough. You cough, I don't cough. Are you sure you don't have COVID? Okay. Hmm. How am I gonna treat me? I should have no business working with you. What? I'm here. What? Yeah, you are. 33, não 33.
Spaghetti.
Yeah.
Take me a sushi, please.
Rico, I'm teaching now, Rico.
That's okay.
If I weren't teaching, I would get that for you.
You can take a break.
I'm taking a break right now. The break is almost over. What we're gonna do? I'm back. Okay, so let's start building a table here, because now we're gonna talk about resistors in parallel. Okay, and I'm gonna put together a table here for you, like that. Let's see, 1, 2, 3, 4. It's gonna be So it's easier. Tables are becomes easier to visualize. 1, 2, 3, 4, 5. 1, 2, and 1, 2, 3. Let's do like that. Okay. Here's gonna be resistors in series. Resistors in parallel. And everything that I wrote down here, okay? Equivalent resistance. Here you go. Equivalent resistance is R1 plus R2 plus R3, right? Then we have, what else? Equivalent resistance. Value of Req. You know, Req is always greater than the largest resistance value. Voltage. Voltage is split among resistors. But the current is always the same. The current is always the same in the circuit that has elements in series only. Okay, and then we're going to do for the resistors in parallel. Let me show you how resistors in parallel looks like. It applies not just to resistors, but to any type of element. It's not moving for some reason. Oh gosh, I hate that. Why it's not doing that? I don't know. This one moves. What about this one here? Okay, finally. It's obeying me. Bold face. Center justified. That's gonna be bold face as well. Center justified. Hey, didn't bold face? Here you go. Okay, now I got it. Let me show you first how resistors in parallel look like. I'm gonna stop sharing my screen so you can see here. Here you go. I have two resistors, right? How can you connect those resistors? Remember, resistors in series, you connect them like that. Touch just one leg to the other, and to the leg of the other resistor, and then you leave those terminals of the resistor to the battery to connect with the battery. For resistors in parallel, it's just exactly what the name means. You connect those two resistors in parallel. All the two ends of the two resistors are connected to one another. That's a resistor. That's how you connect two resistors in parallel. If I want to add a third resistor in parallel, let me get you a third resistor here. There you go. Again, the ends of all the three resistors are touching one another. Now we have three resistors in parallel. Two resistors in series, now three resistors in series. That's the best way to visualize resistors in series and parallel. Okay, here you go. And then I'm gonna connect those resistors in parallel here with my board, my proto board. That's a very useful device that's sold out there in any electronic store. I have a bunch of those proto boards here at home. Some time ago I bought like 10 of those. I thought I was gonna use them, but I ended up not using. Here you go. So I want to connect this guy in parallel with the other one. What I do, I connect here in the same row, so I make sure there is electrical contact between them. Okay. So here you go, two resistors in parallel. If I want to accommodate a third resistor in parallel, I gotta make more room here, right? This wire here is all twisted. I connect on the same row. Here you go. 3 resistors in parallel. And now I can connect my power supply to those two ends. Here you go. My battery. Here and here. I want to make it better. I want to make it easier to visualize or handier to understand and hold it. Here you go. I'm going to give a little bit more of space for everything. Okay, 3 resistors in parallel. 3 resistors in parallel. Battery connected in parallel. I gotta be careful not to damage my elements here. And there's a reason for that. My wire. I got it. Oh. Oh, bye. Here you go. I connected battery to my resistors. Okay. The battery is in parallel with all those 3 resistors, and the resistors in parallel with all of them, all of the remaining ones. That's a circuit in parallel. Oh, so here you go. Let me show you, let me put another row here, because there's another important characteristic that I didn't tell you. Okay, insert. Cells down. Deployment. Adjacent. Adjacent resistor touches only one side. Adjacent resistors touch only one side. Resistors, let's see, resistors touch only one side, one leg of adjacent element. Okay? Resistors touch both legs of the other element, right? Both legs of the other element, right? See? I'm connecting both this side and the other side to the other legs, to the other terminals, not the legs, let's put the terminals. Touch just one terminal, it's better, of adjacent element. Resistors touch both terminals of the other element. That's how you deploy. Let me show you a drawing, a circuit drawing. Let's see here. Items P38. Lab slide. Resistors in series. Resistors in parallel, right in here. So let me show you two. I'm gonna show you only 2 resistors in parallel. Here you go. That's how we illustrate in a circuit diagram. Okay. Resistor 1, resistor 2. You can add resistor 3, 4, and 5, and so on. And now we're going to go through the same thing that went before. The equivalent resistance is going to be different. Okay, so let me put, here you go. I'm going to copy that and I'm going to paste it right in here.
You're not sharing your screen,
I'm
Professor.
not showing. Oh, I'm sorry. Thank you for letting me know. Oh yeah, good idea. I didn't take attendance yet, right, Rico? Raquel, thank you. I'm gonna take it. Resistors in parallel. Let's put that here. Oops. Okay, as an equivalent resistance that is equal. Okay. The inverse. Here you go. The way you do it is like that. The inverse of the equivalent resistance is equal to the sum of the inverse of the other resistors. Huh? What do you think? Like that? You go. You go. Like that. Can you remember? If one is the sum, if you remember the sum, the other one's going to be the sum too, but it's going to be the sum of the inverse. Like that. Okay? Equivalent resistance. We'll put like that. I'm going to put like that. Here you go. And then I will write that down. Equivalent resistance. Equivalent. You know what? I'll leave that like before. I'll leave like before. I'll leave this way. And now here. Like that. Okay? Because now we are taking the inverse value, you know, if the equivalent resistance ended up being greater than the largest value, now it's gonna be less than the smallest value. Okay? I'm gonna put like that, R1. R1 is the smallest. Oh, R1 is the smallest of all resistors. So here you go. Yeah. See, it's doing all the way around. It's the inverse. It's the inverse too, because now the equivalent resistance will always be less than the smallest resistor. What about the voltage? Oh, the voltage is different. It's not the sum of the voltage. It's actually because every element is connected in parallel. The voltage would be the same for every element. Like that. That's an important difference between what one does, the other one. What resistors in series does one way, resistors in parallel does in the other way. Here the current is the same, but not here. Here the voltage is the same. Here the voltage is the sum, but the current in circuits in parallel is different. It's going to be something like that. You know, the total current coming out from the battery is going to be the sum of the currents through each element. There you go. Like that. Do you see here the cross, how it goes? What one does, the other one does in the opposite way. Here you go. It's not gonna be the sum. Equivalent resistance is always greater. No, is always lesser than the smallest resistance in the circuit. Smallest resistance in the circuit. Like that. Ooh. The sum of the the voltages, let's put this way, the voltage across each element is always the same. The net current, the total current is equal to the sum of the individual currents. Like that. Here you go. So the table here, summarize it in a better way of memorizing it. Okay, so let's take attendance, right? Thank you for reminding me, Raquel. Let's see, not this one, it's this one. No, I want something else. Here you go. Oh, CSU. Here you go. While you digest that, today is the 6th of July. Blaze is here, right? Are you still here, Blaze? Okay. Well, I cannot hear you, Blaze, but I'm going to assume you are. Kyla, are you there, Kyla?
Oh, Professor, I'm here.
Okay, good. Thank you. What about
Sorry.
Kyla? Are you there, Kyla?
Here.
Okay. Kyla, okay, good. Courtney?
I'm here.
Okay, next is Christian.
I'm also here.
I cannot hear you, Christian, but that's okay. I see you. Barely hear you. Madeline Childs. Are you here, Madeline? I don't see Madeline here. Next, Cynthia.
Here.
Next, Raquel.
Here.
Okay, Brittany.
Here.
Next, Melissa. Melissa Flores. Let's say you're here, Melissa, otherwise I'm going to assume that you're away from your computer. Here you go, Taylor. Taylor Givens.
Here. Here.
Okay, who's that? I heard two here, two hears. Is that Melissa or just Taylor?
No, it was just me.
Just Taylor. Okay. Okay, next. Let's see, someone's trying to come in. Next, Taylor, Evelyn.
Here.
Evelyn Gomez. Okay, Brittany Gonzalez.
Here.
Jessica Gonzalez.
Here.
Next is Jacqueline Johnson.
Here.
Rhonda.
Here.
Paloma Medina. Paloma, I don't see Paloma here. Allison.
Here.
Okay. Yareli.
Here.
And Brian.
Here.
Okay, so So what's going on here? Did I miss anybody? I'm getting 16 here. There are 17. Yeah, okay. It's just must be Melissa, right? Melissa, are you there? Yeah, I don't hear. I can't hear Melissa. Okay, let me save that. And now we can continue. So let me. Okay, so here you go. Let me see. Yeah, my resistors are getting warm here. Okay, let me disconnect my battery. There is something else about very important about resistors in series, not just resistors but elements in series, okay? And elements in parallel. I'm going to give you an example here. Let's see if I can get a better battery. This one is running out of power. I can't get a better battery, unfortunately. Yeah, that's the only one I have. Need to charge that. Maybe you can still work with this one. Let's see. Okay, I'm going to show something interesting about circuits in series and parallel. Okay. I'm going to connect this resistor to my light bulbs. Here you go, my LEDs. The LEDs are going first to be connected in series, and then I'm going to connect the LEDs in parallel. Something interesting happens for circuits in parallel and elements in parallel and elements in series. Here you go. Okay, so here you go. Let's see. Hopefully I'm not going to burn my LED. Okay, so here you go. See my LED is lighting up? Let me stop sharing so you can see better. My LED is lighting up, right? If I disconnect my resistor, the LED turns off. See that? I connect back my resistor, the LED turns on. What does it mean? It means that elements that are connected in parallel, once they fail, it affects the other elements. If this resistor fails, it's like as though it became disconnected from the circuit. And because it failed, I'm gonna think that my LED failed as well. When in reality, it was the resistor that failed. Okay, here you go. Something like that doesn't happen when you have your element connected in parallel. Something like that doesn't happen. Let me show you. I'm going now to connect the LED in parallel with the resistor. Okay, so here you go. Okay, here you go. See, my LED is working. Right now I'm going to disconnect my resistor. See, my LED is still working. The fact that this resistor failed doesn't affect the functioning of the LED. Okay? Because it's still connected to the battery. So the LED and the battery works as an independent circuit when the LED is connected in parallel to the resistor. Okay? Also notice that the intensity of the LED changes, right? The intensity of the LED changes when I disconnect the resistor. It doesn't matter if it is one LED or two LEDs. Here you go. I'm going to connect this LED in series with the other one. I have two LEDs. That's a type of demonstration that I make in my lab. Here you go. Here you go. Two LEDs in series. They should light up unless I did something wrong or unless I run out. Oh yeah, here you go. I connected in the wrong place. Yeah, okay, this guy is switched. Okay, see that? LEDs in series, right? They are both lighting up. I remove this LED as though as it has been burned out, and the other LED stops working as well. Put it back, both LEDs turn on. Now, if you put them in parallel, okay, here you go, parallel. LEDs in parallel. I'm going to remove one of the LEDs. Okay. This LED is off, but this one becomes on. It is as though this LED had been burned out. But the fact that this LED burned out doesn't affect the functioning of the other one. There's an important difference between parallel circuits in parallel and circuits in series. There's another important difference. Okay, so here we go. Another important difference. Difference between elements in a circuit in series and parallel. If an element, if you have one elements in series, elements in series, here you go, elements in series. If one of the elements fail, comma, all the other elements will not work because the failed element will interrupt the flow of the current throughout the whole circuit. Okay? Elements in parallel if one of the elements fail, all the other elements will continue to work because the failed element interrupts the flow of current only throughout its own branch of the circuit. Okay, you can see that. You saw that in real life, right? Now let's see that in a slide format. Here you go. I'm going to show you first the circuit in series. Right? If this resistor fails, it is as though as we take it out the resistor from the circuit. Okay? Now you have that picture of the electric charges flowing through the circuit. When the electric charge comes at this point here, they cannot jump from this end to the other end. Consequently, the current goes to zero. Okay? The current ends up going to 0. So if you have a light bulb here and a light bulb here, both if this light bulb fails, this other light bulb is not gonna light up either. Okay? Because the electric charges cannot jump from one point to another, right in here. Go back here. But in the case of circuits in parallel, here you go. In the case of circuits in parallel, if this resistor fails, yeah, there won't be any current flowing through here. That's true. But the current still will be able to flow through this other branch. Okay? It is as though the bridge, you have a bridge here and the bridge collapsed. No cars can drive through this branch here of the circuit. Okay? And they choose to go through the other way. It is as though you have a bridge here that collapsed and there cannot be any flow of traffic through here. That's another important difference between circuits in series and circuits in parallel. Okay. So what time is that? 7:15. Man, it's getting hot again here. Let me see if I can get. Yeah, I need some fan here coming through. Okay, so lots of things about the circuits, right? The best ways for you to play with those elements that I have right here: batteries, resistors, light bulbs, LEDs. That's the best way to understand. I think that can you hear the television? It looks like the television is loud, right? Can you folks hear the television there in the background?
I can't.
You can, right? Let me ask to turn down the television. Hang in there. Okay, so the television is lower now. I hope you don't hear that anymore. Okay, resistors in series. Okay, we're gonna put another row here. Element fell. Everything off. Everything turns off. Turns off. Other elements continue working. Okay. So think about that. That's very important. That's very important. Think about that Christmas tree. Christmas tree doesn't have only 2 LEDs. Christmas tree has a bunch of LEDs, 100 LEDs on them. Suppose that someone would decide to connect the LEDs in series in a Christmas tree. Okay? If one light bulb will fail, everything else would not light up. And then you'd be checking among 100 LEDs which one failed. It would be a huge amount of work for you to do that. Okay? Because of that, manufacturers of Christmas tree, what do? They connect the LEDs, all the LEDs, they are connected in parallel. So if a single LED fail, everything else works, and you can pinpoint which one is not working. Make sense? Okay. This is important. This is important. If you are in the business of manufacturing Christmas trees. Okay. If all LEDs, if all light sources were connected in series, and a single light source would fail, everything else, every light source would be off too, and you would have a hard time determining which bulb, right, or LED, which LED failed, because you have 100 of those to figure out. Is this one? Is number 2? Is number 3? Is number 4? Is number 5? Slash LEDs, right? However, if you were to connect all light sources in parallel, only the damaged LED would turn off if it would be turned off, and it would be easier to pinpoint which light source is good or bad. Here you go. Okay? That's so you saw that here in real life, how those things work, right? And that's what we have for circuits in series and parallel. There's nothing else to talk about. Okay. Oh, there is a safety fuses. You can read about that too. Okay. Let's see. That's why safety fuses are connected in series to an element. Okay. Sometimes, you know, safety fuses are there. Fuses exist to protect a given element from a peak voltage or current. If a given current exceeds, if a current exceeds a given limit, okay, the fuse fails to protect the other elements in the circuit. So being connected in series is not that bad. It's not that bad. You can use that to your advantage as well. Okay? You wouldn't want to connect your LEDs in series in a Christmas tree. You wouldn't want to do that. Because if one LED fails, the whole light display would fail too. However, you can use that to your advantage. You can use that in fuses. Sometimes the current in a circuit can have a peak, you know. It's not possible to control the current all the time in a circuit. So if a given current value exceeds, because, you know, a problem in the power line and things like that happens, or because of a storm out there, you may burn an expensive element in your circuit. To prevent that from happening, what do? We put a much inexpensive device in series with your expensive device. And this inexpensive device is called a fuse. They cost less than $1. Okay? that multimeter that you saw, this device right in here that you saw, it has a fuse here inside in case I misconnect the device, connect the device improperly, okay? Especially here in the circuit where I was measuring the current as you saw. So we have fuses all over an electrical circuit. There are fuses all over, even in your house. Okay, and that's what the book talks about. And any questions before we proceed? What's gonna come next is electric power, and the last thing is in this chapter of electricity. Okay. What you know, electric power. Go. What's electric power? Well, it's electric power is the amount of electric potential. Is the amount of energy. Let's put it this way: is the amount of energy, electrical energy spent per unit of time. Okay? That, and what does it mean, electric power? Electric power has units of joules per second. Okay? We abbreviate that as J divided by seconds. This unit shows up so frequently in physics that we give it a name. We call it watts and abbreviate by the letter watt, W. We covered that before, right? Let's see, in the previous, let's see here, watt, power, no. What about power? It doesn't, we didn't cover that in mechanics, right? Yeah, we didn't cover that in mechanics, unfortunately. Yeah. Well, so you're seeing that for the first time. Unfortunately, we didn't cover that in mechanics. Okay? So have you ever heard, the electricity, your electricity bill usually comes how much energy you use, okay? And how do they measure that? They measure that in kilowatt hour, okay? Have you ever heard that? KW-H. Have you heard of that? If you look at your electrical bill, that's how the electrical company measure how much energy you spend, electrical energy you spend at home. This thing here, can be turned into joules, by the way. Yeah. Let's take a look at, let's see if I can find a electrical bill in the internet. Electrical bill. Let's see if they have any electric bill. Let's see. It's who's electricity? Pay your bill. Let's see. Maybe they have a sample of an electric bill. How to read your electric bill. Let's see. Home, pay in person, pay by mail, budget billing plan. Check out the FAQ. Gas payment, log in and pay with your debit card. Let's see here. Electric bill sample. Let's put here electric bill sample. Oh, or maybe they have it here. Oh yeah, here you go. We're there, right? Let's see. Let me see if I can download this guy. Doesn't look like I can download this guy. What a shame. Let me see if I can get that. Ah, gosh. Oh boy, they don't let me download it. What a shame. Adicionar, compartilhar, no. Sample. Let's see. Sample. Okay, good. Now we have it. It's coming. Oh, oh gosh, stuck here. Stuck. Oh my. Let's try this one here. Let's see, let's see. Oh, gonna blow it up. Okay, let's see if we, oh yeah, here you go. See that? Kilowatt hour. Okay, that's how much energy you have used. This unit here, kilowatt hour, can be converted into joules. That's just another way of measuring energy. Kilowatt is the unit of power, of joules per second. You can convert. Kilowatt hour, what's kilowatt hour? It's kilowatt times 1 hour. That's what kilowatt hour is all about. 1 hour is 3,600 seconds. Okay? So let's make a conversion. Here you go. Units of energy. Units of energy, right? Units of energy. There is the joule. There is the joule. There is the calorie. There is the calorie with C, capital C, okay? Which is 1,000 calories with lowercase c. And there's another way also expressing energy in kilowatt hour. Okay, kilowatt hour. They usually without the dash, just like in the. And how are they related to one another? Okay. So I'm gonna do the math here for you. Insert. So you can appreciate how those units are converted. 1 kilowatt hour is what? 1 kilowatt hour is 1,000 watts times hour. Okay? That's what 1 kilowatt hour is all about. And what else? 1 hour is 3,600 seconds. Okay? Which give us 3,600,000. Let's put the commas here. Watts times second. Watts times seconds. Oh. Okay? But watts is joules per second. Watts is joules per second. Here you go. And we end up with what? 3,600,000 joules. 600,000 joules. That's what we get for 1 kilowatt hour. 3.6 times 10 to the 6. Oh. 3.6 times 10 to the 6. Here you go. Ten to the 6 joules. That's what 1 kilowatt hour is all about. Okay? So if you are using 500 kilowatt hour, like that, 565 kilowatt hour, if you want to find out how many joules you are using, you have to multiply 565 by 3,600,000 joules. Okay? So that's the unit of one of the units of electricity. What else you have to know? There is a relationship that I'm not going to derive here for you. There is a relationship between power, current, and voltage. Here you go. Power is equal to the current in a circuit times the voltage. Okay, times the voltage. Like that. And the unit of, from this relationship, we can also say that the watts is the unit of current, which is the ampere, times the unit of voltage, which is the volts. Okay, like that. So let's come up with an example here. Here you go. There's an example here in the book. So here you go, example. Electric bill. So let's say you spend 25 cents. The company charges you 25 cents per kilowatt hour. Let's say, find the cost to operate a 100-watt light bulb for 10 hours. How much electricity you have to pay to operate a 100-watt light bulb for 10 hours. Okay? Let's look at the solution here. I'm going to do the solution here in my favorite software. Alright, so here you go. That's find the cost to operate a 100-watt bulb, light bulb, for 10 hours. If your company, if that DWP, right, DWP charges you 25 cents per kilowatt hour. Okay. Here you go. 25 cents per kilowatt hour. Right? Okay, so here you go. First you gotta find out how much energy you're going to consume in 10 hours. For 10 hours, let's put here. Here you go. Your light bulb. Here you go. Your light bulb will consume 100 watts times 10 hours. Okay? So we do this math here. Calculate. You go. 1,000-watt hour. 1,000-watt hour is what? 1,000 watts is 1 kilowatt. Okay, so here you go. Is 1 kilowatt. I can replace it right in here. Go. So you're spending 1 kilowatt in 10 hours. Okay. This light bulb spend 1 kilowatt in 10 hours. Okay. If you spend 25 cents for every kilowatt, so the cost to operate your light bulb is 25 cents. Okay? The cost, if the cost is 25 cents for every kilowatt hour, the cost to operate your light bulb is only 25 cents. Okay, let's see if that's it is. I'm curious. Is 25 cents is a reasonable rate? Let's take a look there at that electric bill, right? Let me save the scene here first. Electric bill that we saw. Let's see here. Daily usage. No, I don't want. How do I get out of here? Let me see the cost. They have the cost here, the electricity cost. Doesn't look like they have it. Average daily usage, average temperature. They don't. Doesn't look like they have the cost per kilowatt here, unfortunately. But we can find out from the electric bill, right? $113 in June. Oh gosh, see, sign up. I do not know how to get rid of this guy. Let me see. BG price compare. The current price for the standard offer service electricity is 8.85 cents per kilowatt hour. That's how much they charge. Okay. 8.857 cents per kilowatt hour. So it looks like 25 cents was a little bit too expensive for the book. That's what the book is giving me. SOS electricity cost beginning through their weighted average. Well, the price, yeah. So that's how much they, according to this bill, that they charge. Okay. So it looks like the amount here that the book said is too expensive, 25 cents per kilowatt hour. Okay, 7:43 right now. Folks, I covered everything that I wanted. Okay, and do you have any questions? This is a long chapter, there are lots of things, I want to cover lots of things because I think it's important. And any question that you may have. I think it was an interesting semester. I like to teach online, but starting next semester we have to start doing, in-person teaching, right? We'll be seeing each other if you folks are around. Any questions? So let me stop sharing here. Take a look at the correction that I have in there. Let me just remind you of the schedule here, right? Homework 7 is due today. Next class, we are going to have a review. I will prepare the final exam. Don't forget the final exam is all the material. Final exam, everything. Final exam will cover everything. Expect 50% of the material that was not covered in the exam. Okay? In the final exam. I have office hours tomorrow. It's between 4:20 and 5:20. And we can stop right now. If you don't have any questions, we can stop right now. And yeah, you have a question, please?
Yeah, yes. So, after our final exam and our homework 8 on Thursday, by what day will that be graded?
As soon as possible. I'm gonna, let's see, homework 8. Yeah, I'll do that in the weekend. I'll do that in the weekend. And I cannot, the final grade is gonna depend when I get the lab grades from the other instructor, okay? So I depend on receiving the lab grades from the other instructor. I do not know when I'm gonna get it, but once I get it, I will submit everything to you all. You're welcome to send me an email and inquire about your grade. I will upload the grades for you there in your folder, in your personal folder, so you'll be able to find out how you did in the final and the homework.
Do you wait? And my final question is: do you know if during the fall semester for this year, if they're gonna have on-campus classes?
I don't know. I do not know. I do know that my community college is having half and half. Some of the courses are on campus, some of the courses are online. I do not know how CSU is doing. I believe the CSU is still gonna do most of their courses online.
So maybe most of my courses will be Zoom.
Yeah, it's possible. Yeah.
What about is your community college a Harbor?
Yeah, Harbor College. Yes.
Yeah, that's where I went before. So are they open, right? Are they going to be open in the fall?
Yes. But like I said, some courses are online at Harbor. On the fall, it's going to be online, and some courses are going to be in person. Yeah, the courses that I'll be teaching there at Harbor is going to be in person. But my other colleagues are my other colleagues are there teaching online. Here at CSU, let's take a look at CSU. I was looking. I believe that most of the courses is going to be online at CSU. Let me take a look here. I was checking the schedule for the fall. Fall. Let's take a look at physics. See, most of them are alternative. There is this one here. It looks like they're gonna have. I don't know what WH means. Must be the new building, right? No, it's not the new building. That's the new building. Yeah, some of the courses are going to be in person, but most of them is going to be online. See that alternative? Oh, let me share the screen. Take a look here. See that? Most of the courses are alternative. Only a few is going to be in person. Only a few of the courses that are going to be in person. So it depends on the course apparently. Okay, Blaze?
So do I just check which courses I'm taking and it'll tell me whether it's online or on campus?
Yeah, that's right.
So if it says alternative, does that means
online? That means online. That means online because hasn't been assigned a room. See that?
Oh, I see your page right now. Which page are you on right now? I see mostly just PHY.
PHY? What do you mean PHY? I don't see PHY anywhere.
It's under the subject.
It's physics. It's physics right in here. See that? Yeah, it's physics. PHY. Here you go. PHY for physics. I'm looking here at the location. Do you know how to get here? Are you talking about physics course? Which type of course are you referring to?
I was thinking it was earth science. It was one of them.
Okay, well, earth science. You want to know the fall, right? Let's see, earth science. Earth science, earth science, earth science. Yeah, here you go. Let's take a look. Earth sciences. Okay, no, it says PHY. Let me see here. Let me do that again. Earth science again. Didn't accept. Earth science. Here you go. Search. Yeah, EAR. Yeah, most of them. Yeah, alternative. I suspect that alternative means online. I suspect. Okay.
Yeah, okay. Thank you.
See, they said internet here. So now I am a little, I do not know what they mean by alternative. What's the difference between internet and alternative? I suspect that internet is the asynchronous course and the alternative is the synchronous online course. I believe that both of them are online. The difference is here is that as asynchronous and this one is synchronous. Yeah, I believe that's what it is. But that's what we have here for the earth sciences. Okay.
Professor, I have a couple questions in regards to the final exam. So my first question is, will the questions on the exam be similar to the ones on the homework?
Yeah, multiple choice.
Yeah.
Mm-hmm. They're not going to be exactly the same ones. You don't expect exactly the same ones, okay?
But they'll be similar, right?
Yeah, they're going to be similar.
Okay. And then another one of my questions, you mentioned that half of the exam is going to be on material we didn't cover.
Yeah.
But how are we supposed to know what we didn't cover?
Well, it's in the previous exams, right? What you didn't cover. Let's take a look here at this. Let me see. Maybe I put that in the syllabus, right? Here you go. Exam 1, first exam, chapters 1 and 2. See that? Exam
Yes.
1. Second exam, just chapter 3. Third exam, chapters 4 and 5. See that? So
yes.
chapters 6, 7, and 8, is going to be 50% of the final. Okay?
Okay, so just chapter 6, 7, and 8.
Yeah. Mm-hmm.
Okay.
Yeah, 50% of the material. Let's put it chapter 6, 7, and 8 chapters. The ballpark is not going to be exactly right. 6, 7, and 8. Chapter of the materials, chapter 6, 7, and 8, and 50% chapters 1 through 5. Okay, like that. So
do you know how many questions the exam will be? About how many?
Yeah, I'm thinking about 50. Yeah, we have 2 hours. It's going to be 2 hours long, okay? So let me write that down here also in the notes. Final exam. I cannot write everything there in the syllabus. Final exam. 2 hours long. Oh, we can, I'm thinking about, let's see, let's meet what, 5 p.m., right? Let's do half an hour, 5 p.m., 5 to 5:30 p.m. review. Let's do this way. If we need more time, we can extend to 6 p.m., okay? And then between 5:30 and 8:30 p.m., no, not 8:30, sorry, 7:30 p.m., the final exam. So expect 50 questions because since you have more time, right? We can do a little bit more questions there. 25, approximately 25 questions, chapters 1 through 6, and 25 questions, chapters 7. Is that right? 1 through 6. 1, 2, 3, 4, 5. Now 1 through 5, right? Let's take a look here. Yeah, 1 through 5. That's right. 1 through 5, and 25 questions, chapter 6 through 8. Okay. Final exam 2 hours long. Expect 50 questions. Expect a total of 50 questions. A total of 50 questions. Approximately 25 questions, chapter 1 through 5, and 25 questions, chapter 6 through 8. Okay? That would correspond, homework, 25 questions, homework 1 through 5, right? 25 questions, homework 6 through 8. Like that. The number of their homework corresponds to the chapter number in the book. Is that clear?
Yes, thank you.
Okay, let me save that and I will upload to your folder. Let me get the syllabus as well. Here you go, syllabus. That's gonna be version 4. Okay, go. And let me stop also my recording here. Don't forget I'm going to upload my recording. Are you folks accessing my recording?